All right, everyone. Today we're going to be tonight I guess I should say, we are going to be going over square roots. Okay.
All right, everyone.
Um, and We'll take any questions that you have. That is if everybody's not watching the Bucks game. And if you're watching this later, no big deal. Come find me if you have any questions as you're watching through this. So the main key to this entire unit is really problem number one. If you can't handle that problem, it's really quite simple. You probably just need to after you see this problem, if it's not going real well, you probably just need to stop watching and come find me as soon as possible. Okay, because the whole key to number one is being able to put it in simplest radical form. And if you can do that for a single root, most of the other concepts build off of that. Okay. So if you can handle that, you can potentially handle the rest of these. If not, then you probably need to make sure you're reviewing that first. Okay. So putting something in simplest radical form, we have two different possible methods that we can use. One is by making a factor tree. It's not my favorite. And one is by using perfect squares. I'm going to use the perfect squares method first. And I'm going to break up 810 into 81 and 10. I'm using 81 because 81 is a perfect square. So now I can take the square root of it and write it as 9 root 10. Um, excuse me. An alternative option is to use the factor tree method. Okay. And what that involves is breaking down 810 as much as possible using a factor tree. So I've broken it down completely using a factor tree. And I see I've got a 5, I've got a 2. And then what you want to do is you want to create as many pairs of numbers as you possibly can. Okay, because all of those pairs are perfect squares. Okay, so I'm going to rewrite my 810 as 3 squared times 3 squared times 5 times 2. Okay, so anything that I could group as a pair, I put together. Anything I couldn't, I didn't. I'll stick a square root over all of them because they were all a part of 810. I'm just breaking up 810 into those smaller numbers. Then, everywhere where I see the squared, they cancel each other out. Square roots and squareds are opposites. The 5 and the 2 don't come outside of the square root because they're not perfect squares. Then I multiply my things back together. 3 times 3 is 9, 5 times 2 is 10, and I get the exact same thing that I did above. Okay? And that's it. I mean, I'm hoping that was at least pretty straightforward. Okay? Next, we're going to deal with multiplication. Okay. And here's what you got to do for multiplication. Multiplication, you have a couple different options in terms of simplifying. For a lot of these, there's a couple different ways you could go about it. I'm typically just going to show you one way, but if you got to the same answer in a different way, it's definitely very possible that you're all good there. Okay, so the way I'm going to do it is I'm looking at 18 and 30. I could simplify the square root of 18. So I'm actually going to do that first. I'm going to break it up into 9 and 2. And then I'm going to change that square root of 9 to a 3. Okay, so I use perfect squares method to break down the square root of 18. And then I'm going to leave the 3 root 30 alone. And I left the 3 root 30 alone for one simple reason. There's not a perfect square that goes into 30. Okay. Now I'm going to use my rules of multiplication. So I can multiply the outside stuff together. So my two threes can multiply together to get 9. And my two numbers inside the square root can get multiplied together as well. And they make 60. Now I've just got to take a look at what I've multiplied together and decide, can I simplify it anymore? Well, 60 can be divided by 4, and 4 is a perfect square. So yes, I can. Take the square root of the 4, and I get 18 root 15. There are certainly many other ways that you probably could have handled that. But that was kind of the way I chose to do it for that one. In the end, if you got 18 root 15, you're in great shape. For the addition problem down here at number 3, um, the entire key there is you can't add any of those together in their current state. There's no way to do it. So what you need to do is you need to simplify each of those square roots. Okay. And then if after you simplify them, you end up with the same number under the root, then you can combine them. If you don't, then you can't. So I'm going to simplify each of these using the perfect squares rule because for me that's faster. If you needed to make a factor tree for any of these, that would totally be okay too. But I broke my 175 into 25 and 7. I broke my 8 into 4 and 2. And I'm going to break my 128 into 64 and 2 as well. Now I'm going to take the square root of those perfect squares. Notice how the coefficients, so those numbers that were on the outside, I'm leaving there the entire time. So that -3 that's in that first one stays there. The 3 that was in the second one stays there. And the 3 that was in the last one stays there. So all I did in that step is take the square root of each of those numbers. So I took the square root of 25, I took the square root of 4, and I took the square root of 64 as well. I'm going to do sorry about that. I'm going to do the multiplication now. So I get -15 root 7, 6 root 2, 24 root 2. And at this point, I'm just looking to see where are my like terms, okay? So 6 root 2 and 24 root 2, those are the only ones I'm allowed to add together because they have the same number under the root. 6 and 24 add to 30, I get 30 root 2. And that's it. That's our final answer. On to number 4. So for number 4, it's a little bit of a different problem in that there's nothing actually wrong with either the square root of 15 or the square root of 10. Both of those are actually as simplified as you could possibly make them. However, we are not allowed to have a square root in our denominator, so we need to get rid of that. There's a couple different ways you can handle this problem. I'm going to show you the way that I would choose to handle it. You are allowed to divide and simplify numbers that are underneath a square root. Okay, so I can simplify the 15 over 10, and I can make it 3 and 2. Then I need to get rid of that square root that's in the denominator. So I'm going to multiply my numerator and my denominator by the square root of 2. I get 4 root 6 over 5 times regular 2. Okay, so when I multiplied the square root of 2 times the square root of 2 together, those made a regular 2 because they created a perfect square. Basically, square root of 2 times square root of 2 is 4, and the square root of 4 is 2. I just don't need to show all that work. If I multiply two of the same square root together, the square root part cancels out. I get 4 root 6 over 10 from multiplying the 5 and the 2 together, and the 4 over 10 simplifies to 2 and 5. If you did it a different way and you ended up with 2 root 6 over 5, you're in good shape either way. Okay, now some slightly trickier problems. So over on number 5, you're basically just combining knowledge a little bit. You're combining your knowledge of multiplying polynomials, in this case a binomial times a binomial, with multiplying square roots. You're going to take the square root of 3 and you're going to distribute it. You're then going to take the square root of 2, and I'll do that one in a different color just so we can kind of see maybe at least a little closer where I'm getting things from. You're going to distribute that too. Distributing the square root of 3, I get -3 square root of 9 plus the square root of 6. So I just multiplied the square root parts together. I'm going to do the exact same thing as I distribute the square root of 2. And I get -3 root 6 plus root 4. Now I've just got to do any simplifying and combining of like terms where I can. So at the very beginning and end of my problem, so right here and right here, I've got some perfect squares. I'm going to turn the square root of 9 into a 3, and I'm going to turn the square root of 4 into a 2. In the middle, those are like terms. Now, be very careful when you're adding those together because I have a regular square root of 6 here. Remember, there's a coefficient of 1 there. So 1 plus negative 3 is negative 2. So I get negative 2 root 6. 3 times 3 is 9. And my like terms in this case are just the numbers. So I'm going to put negative 9 together with 2, and I get negative 7 minus 2 root 6. So really all we were doing there is distributing the square root of 3, distributing the square root of 2, and then just combining some like terms. You may have shown a lot less work, or your work may have looked slightly different. Again, in the end, if you got to the same place, you're in good shape. Number 6 is one where we actually don't have a significant amount of choice in how we can attack that problem. Okay. The major problem we have is that there's a square root in the denominator. You cannot multiply the numerator and denominator by the square root of 3. If you do that, you would have to use the distributive property on the bottom. And the issue with that is it would give you a square root still somewhere down in your denominator, and that's not going to work. Okay. So what you have to do is you have to multiply by what's called the conjugate. And here's what that looks like. You're going to take your expression from down in your denominator, and you're going to multiply by that exact same thing, except you're going to switch that middle symbol. So instead of multiplying by 4 plus root 3, you're going to multiply by 4 minus root 3. On the top, I'm going to do the distributive property. So I get 16 minus 4 root 3. No, I can't multiply the 4 and the 3 together. On the bottom, you could shortcut it. And if you kind of know how you could shortcut that multiplication, feel free to do so. I wouldn't recommend it, though. I'm going to FOIL just like I did above. So I'm going to distribute the 4, 16 minus 4 root 3. And I'm going to distribute the root 3. I get 4 root 3 minus the square root of 9. Now, it looks like I made something that's significantly more complicated, but I really didn't. On the top, I keep 16 minus 4 root 3. On the bottom, I'm going to kind of do a quick couple things at the same time here. When I combine those two like terms in the middle, they cancel each other out. When I take the square root of 9, I get 3. And 16 minus 3 is 13. That's my final answer. Okay, so again, for those, if you have addition or subtraction in your denominator along with your square root, again, what you have to multiply by is called the conjugate. Okay, and the conjugate is, again, that same expression that's in your denominator, except for with the opposite symbol in the middle. Doing that will make sure that when you multiply that all out, those two middle terms cancel each other out. Okay, now for number 7, last one before we do an equation solve. Okay. We're going to break up the square root of 48 into a 16 and a 3. When you have variables underneath your square root, all you need to do is create as many perfect squares as possible. The only way to assure that is to make sure you have something that actually says like x squared or y squared. In this case, we actually have an x squared and we have just a regular y, so there's no need to break them up. We're going to take the square root of 16. The square root of 3 we can't do, so I'm going to leave it under the square root. The square root of x squared is x. And the square root of y we can't do either, so we're going to leave it also under the square root. I'm just going to stick it back under there with the 3. Okay? Now, the one thing we have to make sure we add is because we took a square root, anytime we take the square root of a number, let's say the square root of 25, square root of 36, all of those are positive number answers. Okay? So because we're not sure whether x is positive or negative, we got to force it to be positive. So we're going to put absolute values around it. Okay. The really quick shortcut there is if you're taking the square root of a variable, okay, and something comes from inside of a square root to out, you just got to assure that it's positive. You do that with absolute values. Last but not least, the equation solve. When solving an equation, the first thing you need to do is isolate the square root. So I'm going to do that by subtracting 5 from both sides. Once you've gotten the square root all by itself, then what you need to do is you need to square both sides to get rid of the square root. So I'm going to square this side, and I'm going to square this side. What I get over here is 64. Over on the square root, squaring a square root simply cancels it out. That's all it really does. So that's just going to turn into 11k minus 2. At this point, I've gotten rid of the square root. All I'm doing is solving for k. So I'm going to add 2 to both sides. I get 66 equals 11k. I divide by 11. I get k equals 6. Okay. And that's really it for solving. There was one question that popped up in the chat that I'm going to try to address now. Jackson asked, so if you have an X and or a Y, it doesn't change the problem that much other than just adding it onto the end of the thing. Kind of, sort of. So like looking back at these variable ones, like let me just quick give another variable example because we might as well. So to partially answer Jackson's question here, it doesn't change what you do at the 48. So like if you look back up at that problem, it doesn't change at all what you do at the square root of 48. I was going to break that up into 16 and 3, whether there were variables there or not. That part was not at all going to change. Okay. The part that does change is you're just going to have to adapt what you do based on the variables and the amount that you get in there. So for example, if I had the exact same problem, a square root of 48, but instead I had an x to the 5th and a y to the 4th, here's how I would break it up. I would still do 16 and 3 for my 48. That piece does not change. Again, those variables have absolutely no effect on how you break it up in terms of the numerical values. Okay. But the way I'd break up the variables was different. I didn't actually really need to break up the variables all that much in that first one because there was nothing I could do to change the problem. Okay. But what I could do for x to the 5th is I could break it up into x squared, and x. I could break up my y to the 4th into y squared and y squared. Okay, basically every time you're creating one of those squares, you're creating something you can actually take the square root of. Okay, so I'd still get a 4 from my 16. But then for each of those x's, so like for my first x squared, I'd get an x. For my second x squared, I'd get an x. From this y squared, I'd get a y. From this y squared, I'd get a y. And I'd have a 3 and an x both still left under my root. Okay. And then I would just combine those all together and I'd get 4x squared y squared with a square root of 3x at the end. Okay. So hopefully I did at least a halfway decent job of answering that question, but really to shorthand it, it doesn't ever change what you do with the numbers, but what you do with the variables is you just create a bunch of things with squared in it. Okay. And you're just breaking it up depending on how many you have. Okay. And there's ways that you can kind of shortcut that process a little bit too, but that's kind of the main explanation there. If you're watching this later and any other questions came up, definitely let me know. Thanks for watching and hope this helped.